Here we consider two other kinds of transformations of functions that involve either stretching the graph of a function horizontally or vertically, or involve reflecting the graph of a function in either the x-axis or the y-axis. So let's take some function f of x as shown in red here, and let's consider what the graph of a function g of x looks like, where g of x is defined to be some constant k times the function f of x, where k is a positive constant that's greater than 1. This means that for any input value x, the value of the function g of x is equal to the value of the function f times this constant k, which is greater than 1. This means that the graph of g of x is going to look just like the graph of f of x, except it will be stretched vertically by a factor k. Now, because we're stretching by a factor of k, in other words, we're multiplying the function by k, the amount of stretching will be largest where the function f of x is largest. So in this particular example, the function g might look something like this. Notice that the function g no longer has the same shape as f because it's been stretched vertically to different degrees depending on the value of x. Now consider what would happen if instead the factor k was positive but less than 1. So we define a new function g of x is equal to k times f of x, but now k is a positive constant that's less than 1. In this case, all of the y-coordinates in the graph of f of x are going to be compressed by a factor of k. Furthermore, because we're multiplying by this factor of k, the amount that the graph is compressed will depend on the value of f. So in this particular example, g might look something like that. And again, notice that the shape of the graph has changed. The amount of compression is greater for values of x where the original function f of x is higher. Now let's take our function f of x again, and instead we're going to define a new function g of x that's equal to f evaluated at k times x. So we take our factor k, we multiply the input value by that factor, and then we operate on that with the function f. And again, let's first consider the case where k is greater than 1. Let's now determine what the graph of g of x looks like. To do so, let's take a particular input value, say x equals 5, and we'll consider what the value of the function g is at this point. Well, according to our definition, the value of the function g at a value of x equals 5 is simply the value of f evaluated at k times 5. And because k is greater than 1, we can locate k times 5 on the horizontal axis here, and it's going to be located somewhere like that, to the right of the value 5. Now we can recognize this distance here as exactly equal to f evaluated at k times 5, and so the graph of the function g of x is going to attain that height, but for a value of x of 5. So in other words, the graph of g of x is going to go through that point there, because that point has x coordinate 5 and y coordinate f evaluated at k times 5. Now let's do a similar calculation for a larger input value. Suppose we take a value of x of 10. What is the function g evaluated at x equals 10? Well, again, according to our definition, the value of g is equal to the value of f evaluated at k times 10. And again, we can locate k times 10 on the horizontal axis here. But the distance we move to the right when starting at the point 10 is going to be larger than the distance we had to move when starting at the point 5 because we're multiplying by this factor k. In other words, as we consider larger and larger values of x, when we multiply by k, we get a larger and larger difference between that and the starting value. Now we can recognize this distance here as equal to the value of the function f at k times 10, and the graph of our function g is going to attain that height, but for an x value of 10. So in other words, the graph of g is going to go through this point here, because that point has coordinates x equals 10 and y equals f evaluated at k times 10. You can see that this type of transformation is similar in some ways to the horizontal translation that we've seen before, except that now the distance that each of the points on the function f of x gets shifted to the left is going to be different for different values of x. It's going to be a small shift to the left for small values of x and a larger shift to the left for larger values of x. And what this means is that rather than just translating the function to the left, it's going to compress the function towards the left. And so the function g of x might look something like this. It will no longer have the same shape as the function f, but instead it's going to be compressed to smaller values of x. Now, it's probably not hard to convince yourself that a similar sort of thing happens if we were to instead define our new function g of x to be f evaluated at k times x, but where k is a positive constant that's less than 1. We can follow a similar procedure. Let's imagine what happens if we were to substitute the value x equals 5 into our function g. Well, our function g evaluated at x equals 5 is equal to our function f evaluated at k times 5. And we can locate k times 5 on the horizontal axis here. It's going to be something that's still positive, but it's going to be to the left of 5 because now k is less than 1. And we recognize that this distance here is f evaluated at k times 5. Now the graph of our function g is going to attain that height, but at a value of x equals 5. So in other words, our function g is going to go through that point there because it has an x coordinate of 5 and a y coordinate of f evaluated at k times 5. And we can do a similar thing when substituting in a value of 10 into our function. G evaluated at x equals 10 is going to be equal to f evaluated at k times 10. And again, we can locate k times 10 on here. It will be to the left of 10, but the displacement to the left of 10 will now be larger than the displacement was to the left of 5. Again, because we're multiplying k by larger numbers. Now we recognize that this distance here is exactly equal to f evaluated at k times 10, and we know that the graph of our function g of x is going to attain that height, but for a value of 10. So in other words, the graph of g of x is going to go through that point there because it has an x coordinate of 10 and a y coordinate of f evaluated at k times 10. And you can see this has a similar flavor to the other horizontal translation that we saw earlier, except again the distance at each point on the curve f of x gets translated is different. The translations are larger for larger values of x than for smaller values of x. And so the curve is going to look something like this. The curve no longer has the same shape as f because values of x get stretched to the right, and high values of x get stretched further to the right than low values of x. The final type of transformation of functions that we'll consider is called a reflection. And there are two kinds of reflections that we'll consider: reflections in the horizontal axis and reflections in the vertical axis. Again, let's consider some function f of x, shown in red here, and let's define a new function g of x to be equal to the negative of that function f of x. What does the graph of g of x look like? Well, for any input value x, the magnitude of g is the same as the magnitude of f. The only difference is that the sign is different. So where f of x is positive, g of x will be negative and vice versa. So for this particular input, for example, let's call it x1. If f of x equals 2, then g of x is going to equal minus 2. And so it will go through that point there. If we consider another value of x out here, if f of x has an output of 4, then g of x is going to have an output of minus 4. So it will go through this point here. And so you can see overall the graph of g of x is simply going to be a reflection of the graph of f of x in the horizontal axis. So this is our function g of x. Finally, let's consider a case where we're dealing with a reflection in the vertical axis. So again, let's take this function shown in red here, f of x, and let's consider a new function g of x defined to be f evaluated at the negative of x. So in this case, what we do is we take the input value of x, we change its sign, and then we evaluate that with the function f. That gives us our output for g. What does the graph of g look like? Well, let's take an input value of x equals 2, for example. The value of the function g at x equals 2 is equal to the value of the function f when evaluated at x equals minus 2. So if we locate the point minus 2 on the horizontal axis, we recognize this distance here as being f evaluated at minus 2. And so the graph of the function g is going to go through this point here because that point has an x coordinate of 2 and a y coordinate of f evaluated at minus 2. In a similar sort of way, we can ask what's the value of the function g at an x value of minus 2? Well, again, according to our definition, the value of the function g at x equals minus 2 is the same as the value of the function f when x equals 2. And so we can locate that distance here. This distance here is exactly f evaluated at 2, and so the graph of the function g is going to attain that y value, but for an x value of minus 2. In other words, it's going to go through this point here because that point has an x coordinate of minus 2 and a y coordinate of f evaluated at 2. And you can go through a similar argument for any input value of x, and what you will end up with is a reflection of the graph of f of x in the vertical axis. So the graph of g of x is going to go through that point and look something like that.